This is Math 139, Section 1.2b. It turns out that some things, including the domain and the range that we were just talking about, are actually easier to see on a graph than they are to kind of imagine or talk about without looking at the graph. So in this part, we're going to take a look at some graphs and see what they tell us. We'll start with a few definitions, some things that graphs can tell us. A couple of these, again, we're already pretty familiar with. The domain, all the values of the independent variable, often x when we think algebraically, but it could be something else. Range, all the values of the dependent variable. We typically think of those as the y's. And the domain and range, we can look at the graph and just say, hey, what x values actually have points on this graph? Or what y values actually correspond to points on this graph? Next, we have local maximum and minimum points, which are the highest and lowest points on the graph within a certain local area. I like to think of the local maximum as being the top of a hill and the local minimum as being the bottom of a valley. If I had a graph like this, I would be able to say that I have a local maximum, right here because that is the top of a hill. And I would have a local minimum right here because that is the bottom of a valley. Notice it's not necessarily the highest point on the entire graph. This graph actually goes up forever, so it gets bigger. But locally, it's the largest y value. It's the top of its hill. Next, we have intervals of increase and decrease. These are intervals, and we will use our interval notation here. And they are specifically intervals of x values, and that's really important, for which the graph is rising or increasing, and where it's falling or decreasing. So if I have a graph doing this, my graph is increasing. If I have a graph doing this, my graph is decreasing. Notice that when we talk about increasing and decreasing, we always think of reading our graphs from left to right. It's increasing as I will go from left to right, or it's decreasing as I go from left to right. All right. The next few definitions involve intercepts. Intercepts are simply the points where the graph crosses the axes. So if I have a graph like this, then the y-intercept is just the place where that graph crosses the y-axis. Notice at that point, the x value is actually 0. So x is 0, and then there's some y value at that y-intercept. The x-intercept is where the graph crosses the x-axis, and that would be down here. Notice on this point, there's some x value, but the y value is 0. In fact, algebraically, the idea that one of the variables is 0 is actually the way that we calculate intercepts. If we want the y-intercept, we let x be 0. And if we want the x-intercept, we let y be 0. And we've mentioned that over here as well. always like to think of intercepts or finding intercepts by think opposite variable equal to 0. If I want the y-intercept, I set x equal to 0. If I want the x-intercept, I set y equal to 0. So it's always the opposite variable that I'm going to set equal to 0. All right. The zeros of a function are the values of x that make the function equal to 0. That is, the zeros of the function f of x have to make the function equal 0. They're the solutions to the equation f of x equals 0. Well, gosh, if f of x equals 0, isn't that the same as saying y equals 0? And when y equals 0, that's what we were calling our x-intercepts. So in fact, in some ways, this is just another name for the same thing. Oops, sorry, my paper's slipping there. There's a small difference that we'll talk about in just a minute. But essentially, because we are looking for the zeros, the places where the function is 0, that's like saying y equals 0, which is nothing more than the x-intercepts. So how would you find the zeros based on a graph? You just look for the x-intercepts. There is a subtle mathematical difference between being asked for an x-intercept and being asked for a 0. The x-intercept is actually a point, x comma 0. The 0 is just the x value itself. So if my x-intercept was 5 comma 0, then the 0 would just be 5. Essentially, once you have one, you really know the other as well. All right, let's look at a graph and see if we can find some of these things based on a couple of graphs. We'll start with this one, y equals f of x. And I'm going to begin by asking for the domain and the range. Notice in this case that this graph continues to go on forever. What we're seeing here with these arrows is a graph that's going to continue to go up in that same direction forever on the left side, and again up in that same direction forever on the right side. That means that no matter what value I pick for x, it will correspond to a point on the graph. If I just pick some x value, I'm going to go up, but I'm going to hit the graph somewhere. Even if I picked it way out here, if I went up, eventually this would go up high enough that I would have a point on the graph. So my domain is going to be all real numbers from negative infinity to infinity. Now what about the range? What about the y values? The graph does go up forever, but there's a whole bunch of y values that we never hit on this graph. We never have any y values down here. There are no points down here. In fact, the smallest y value on this graph right here is 4. So my range is going to go from 4, and I think I do include the 4. It looks like I actually hit that point. And then it's going to go up to positive infinity. No y values are smaller than 4. All right, the next thing we want to know is what is f of 3? We're being given the x value 3, the input here. And we would like to know what y value goes with it. So I'm going to go 1, 2, 3 for x. And I'm going to go up, hits the graph right there. And it looks like the y value at that point is 5. Now, I already gave you the x, the 3. So the answer I want is not the 0.35, but just the output, just the y value. 5. In part D, we'd like to find x so that f of x equals 7. Now this time, I haven't told you x, I've told you f of x. In other words, I've told you the y value. You need to come up with the x. So let's see, 5, 6, 7 would be about here. And I'd like to know, where in the graph do I have a y value of 7? Well, there's actually a couple places. If you kind of imagine going across from that 7, notice that there are 2 places on the graph that have a y value of 7. This one right here, which is the point 5, 7. And then this one right here, which is the point negative 1, 7. Now again, I already told you why, so you don't have to tell me the whole point. I'm looking for the x values. So one possibility is x equals negative 1. Another possibility is x equals 5. So that particular question has 2 possible answers. All right, local maximum points. I don't see any local maximum points. There is no place on this graph that looks like the top of a hill. So I'm simply going to say none. There is, however, a local minimum. This point right here is at the bottom of a valley. And that point happens to be 2, 4. All right, the next thing we're asked to find are the intervals of increase and the intervals of decrease. Let's start by just identifying the parts of the graph that correspond to increase and decrease. We always read our graph from left to right. So going from left to right, through here, my graph is decreasing. As I go from left to right, it's falling, it's going down. The answer I actually want to give in the problem are the x values that correspond to this graph decreasing. So let's see, it decreases till we get here at 2. Sort of the shadow on the x-axis would be all of those x values. So my graph is actually increasing from negative infinity to positive 2. Those are the x values that correspond to the falling graph. With an interval of increase or decrease, we always use parentheses, never brackets, because right at x equal 2, the graph's not really falling or rising. It's kind of switching between the 2. So we don't include the 2. All right. The other side of my graph, starting at 2 and going on, is increasing. And again, the answer that I actually want to give are the x values that correspond to the part of the graph that's increasing. So from 2 on up, I've got x values that correspond to that increasing graph. That would be from 2 out to positive infinity. Okay. And you know what? I just realized that I wrote those in exactly the wrong spaces. I'm sorry about that. I didn't read the problem carefully enough. This was increase and decrease, and I did it the other way around. We wrote the interval of decrease here, and the interval of increase here. My apologies. All right. Finally, we want to look at intercepts. We start by asking where are the x-intercepts. And if you look at this graph, you might notice that it never crosses the x-axis. So there are no x-intercepts. The y-intercept, however, there is one. Right here, our graph crosses the y-axis. So the y-intercept would be the point 0, 6. All right, lastly, I wanted to know the zeros of the function. The zeros of the function are where y equals 0. They correspond to the x-intercepts. And since there were no x-intercepts, that also means there are no zeros for this function. All right, let's try one more. Here's our new function, f of x. I'll call your attention to the fact that there's a solid dot on this point. It doesn't go past that solid dot. But there's an arrow on this side. So it does continue to go down and to the right over this way. That means that when I look at the domain, the smallest x value that has a point on this graph right here would occur at -7. Then all the x values from there on will continue to correspond to points on the graph. This is a solid dot, so I will include the -7. On and on to infinity. The range. In this case, when I think about the y values, there are not all possible y values on this graph either. Right? There's no y values, no graph up here for these larger y values. In fact, the largest y value on this graph occurs right here at y equal to 2. So all of the y's are less than or equal to 2. If I'd like to write that in interval notation, I always have to think about what it would look like on a number line. It would go from -infinity to 2. Always reading our interval from left to right. All right, the next thing we're asked for is f of 9. We're being given the x here, and so we want to find the y. When x is 9, we're at this point. Looks like we've got a y value of -6. And again, I don't ask for the whole point. I've already given you the x. You just tell me the output, or the y value, which is -6. In the next one, we would like to know what is x that gives us an f of x of 2, a y value of 2 is right here. If you kind of think of everything that's at that height, this time there's only one point that actually hits that y value of 2, specifically this point right here when x is -3. So y is 2 when x is -3. All right, this graph has got more than one local maximum. The point that we were just talking about, -3, 2, is definitely the top of a hill. So it's definitely a local maximum. And it's the whole point, so this time I'm going to give you the entire point, negative 3, 2. But there's another local maximum as well. Here's another point. That's the top of a hill. It happens to be 8, negative 5. Those are both local maximum points. Local minimum points, I'm only seeing one of those. Bottom of a valley occurs right here. And that's at the point 4, negative 9. All right, let's talk about, see if I can get it right this time, increase and decrease. And we'd like to start with places where the function is increasing. That means the graph is rising as I look from left to right. Let me begin by just drawing on the graph. Through here, I definitely see a rising graph. This is increasing. Then it decreases for a little while, but then there's another part over here where I see a rising graph. Once again, this is increasing. Now remember, when you give the intervals of increase, you only want to give the x values, sort of like the shadow of those places on the x-axis. So when I look at this first section where the graph is increasing, I'm going to notice that on the x-axis it goes from negative 7 to negative 3. I never include the endpoints when I'm talking about increasing and decreasing. This section over here goes from x equals 4 to x equals 8. So there were 2 intervals of increase. All right, what about the intervals of decrease? Graph is decreasing through here, falling, and again over here forevermore, also falling. So we've got 2 sections where the graph is decreasing. If I list my intervals of decrease, once again I'm only interested in the x values. So from here to here would correspond to the x values between negative 3 and positive 4. Over here, it starts to decrease again when x is 8. And then it's going to continue to decrease forever after that. So from 8 to infinity. Okay. By the way, we kind of make that assumption that it decreases forever. You might ask, well, what if it starts increasing again after I can't see it anymore? Mathematicians kind of have the agreement that when we put an arrow on the end of a graph like this, it kind of means we've shown you everything interesting. That graph is going to continue to go down forever. If it didn't, I couldn't use that notation. All right, let's finish up with some intercepts. There are a couple of x-intercepts this time. We can see that there's an x-intercept over here. At negative 5, 0. And again here. At negative 1, 0. The 2 places where the graph crosses the x-axis. So I'll list both of those as x-intercepts. The y-intercept, there's only one. Actually, actually there only ever can be one, otherwise we wouldn't have a function, right? Wouldn't pass the vertical line test. And in this case, it's right here at the point 0, -3. All right, finally, the zeros. These are the places where y equals 0. And that's exactly what I found up here, the places where y equals 0. Therefore, I already know the answer to this question. The zeros are -5 and -1, the two x values that make y become 0. Again, these are very closely related. They're just written slightly differently. The x-intercepts are actual points on the graph. The zeros are the x values where y is 0, or the x values of those x-intercepts. All right, that brings us to the end of section, or part B rather, of this section, and we'll stop there.